right?
You don't have Brian.
Huh? Why? Were you sick? What was the problem? Huh? Are you saying diarrhea? That's fine, that's fine. I didn't need that much information, but that's fine. No, I think diarrhea. Really? Alright. Yeah. Yeah. Did you eat something bad? What did you eat? Huh? Ah, okay. Bad noodles.
Bad noodles.
Yes, which were also bad noodles because they made him sick.
All green. I don't like spice.
Continue. Interference. You got that? Yeah. So now we have 1, 2, 3, 4, 5, 6, 7. Yes. Was he in earlier?
No.
This is your first class?
Yeah.
At 1 o'clock?
Yeah.
You lucky guys. Nice. Alright. A good bit to look at. Interference is when two or more waves combine to form a new wave. So this property or this phenomenon, you must have at least two waves and they must be coming together. And what happens is the two waves come together and they form a new wave. Now you might think, well, obviously. Well, no, not obviously, because for example, if I have two cars and they crash together, I do not make a new car.
Yeah.
That is a combination of the two old cars, okay? So for waves, they still stay waves even when they crash into each other, and in fact they become new waves. So interference is when two or more waves combine, and the principle of superposition states that the net amplitude of the new wave at each point is the sum of the amplitudes at the individual waves. So in other words, if you have two waves and they come together, the new height will equal the old heights added together. As simple as that. So if this wave is coming in at a 1 meter and this wave comes in at 1 meter and they both meet together, then the new wave will have a height of 2 meters. Again, this is obvious, but it's not true for everything. Yes?
Because transverse and
yeah, longitude. We're talking about. Do you know how it actually works for both waves? Yeah.
Well, wave cover another wave.
What do you mean by another wave? Like another.
I mean the same path.
There's only two: longitudinal and transverse. Yeah.
It's not how high.
Huh?
One is lower, one is higher.
Oh yeah. So like if this was 1 meter and this was 2 meters and they come together, it'll be 3 meters.
Oh, 3 meters.
Yeah, not 2 meters. Okay, please write this definition down carefully, and you do need all of it, I'm afraid. I really like this TV now. I think it's so much better.
Why do we turn off the light?
Habit.
Actually, no one turned on the light.
When they come out, like, should I turn on?
Do we need it on? It's a bit dark in here, isn't it?
Yeah.
But it's much better than.
It's easier to read with it off? Okay. Continue?
Teacher, how do you fix ice problem?
What problem?
Ice problem.
Ice problem?
Yeah, like.
It sounds like a joke. Is
No,
it a real question?
No, because I feel like my eyes is getting worse and worse. I don't know why. That's the reason.
Yeah. There's certain activities that cause blindness.
Oh.
What do you think I'm talking about? Of course I mean like using the computer and watching TV too much. What did you think I was saying? Okay. Don't know what you're talking about. Alright, continue. We got this? Do both your parents wear glasses?
No. No, none of them.
None of them?
Yeah.
Grandparents? I mean, not when they were older, would you know?
Oh, then I have no idea then. At least I know they
Have you
don't
got
have-
brothers and sisters?
Yeah, my
Did I-
sister don't.
Ah, so you just got unlucky.
Yeah, even still my sister has sharp eyes. Like really sharp eyes, like an eagle eye.
Oh, it's pointer.
So this sounds like bad luck, I'm afraid. Sounds like bad luck. Okay, continue. Yeah. So basically, the heights of the waves add or subtract. So here's a very simple example. Here's one wave, and here's wave 2, and they combine together, and here this height would add with this height, so it's a little bit bigger. But notice when you get to here, this height adds with this height, but this height's a minus, so that's why it actually starts to go back down. Now here it gets very tall, and we have another crest here, so the two of these together should be the highest. Can you see? So it's actually, the combination is just a simple math combination. It's H1 plus H2 equals H3. If you can, I would like you to draw this with the definition, please. And what's very interesting is the opposite. Yeah, Fourier series is what allows you to start from the result and write it as a simpler waves.
It's so hard for education.
It's extremely hard. I studied it in second year at university.
I was watching YouTube and completely no idea.
Yeah. And did you know, JPEG files, JPEG image files, they make use of Fourier series for compressing the data. Because I remember in university, when we were doing this in class, I said to my friend, using this would be a very good way to make pictures smaller. And he said, yeah, that's what the JPEGs do already. I'm like, oh, someone stole my idea. Okay, you got that drawn?
No.
Ah, come on.
That's right.
Yeah? Continue? So, more definitions, I'm afraid. We say two waves are coherent if they have a constant phase difference and... Okay, so before doing that, do you remember what phase difference is?
Yeah.
The time between the wavelengths. As long as that's constant and they have the same wavelength, we say they're coherent. These are coherent waves.
They have constant phase difference at every point.
Yeah, in other words, if you time the difference between the crests as each crest passes, it should be the same difference.
So they have the same frequency. In order to allow them.
Must they have the same frequency? I don't know if they must have the same. I mean, they probably do have the same frequency, but I'm trying to think if they must have the same frequency. Okay, so if I just said this, they have a constant phase difference. That doesn't mean they have the same frequency, because perhaps their wavelengths are different in such a way that it can make up for the frequency being different. You know, like the V equals F lambda. So I suppose if the F was bigger and the lambda was smaller, the wave could be moving at the same speed, and you could keep the crest together. Do you know what I mean? But anyways, it doesn't really matter here, because for coherent they have to have the same wavelength, which I guess then forces it to have the same frequency. Definition-wise, anyways, Lee, it's constant phase difference and same wavelength. So in the exam, if they ask you what's coherent, it means you have these two things. Here's an example picture. So if you look here, here's the peak of the crest of the first wave, and here's the crest of the second wave. So you notice that they're this distance apart. Later, they're still the same distance apart, that they keep a constant difference. Because this is light, they're moving at the same speed. So it means that the time it will take will be the same, because it has the same distance to cover. And also they have the same wavelength. So here the wave is from here to here, and then if you look at this one, it's from here to here. So you can see that it's the same wavelength, and then the same the constant phase difference. So then we say these two waves are coherent waves. Yeah. Is it clear from the picture? Now, if the two waves were exactly the same, they would be coherent, because if they're exactly the same, they have the same wavelength. And what would be the phase difference? 0 seconds. Most often, guys, just before you draw the picture here, most often in the exam, when they give you a question with coherent waves, they're in fact identical waves. Like 99% of the time. Okay, please add this picture to your definition. Got that? Continue?
No.
Not yet? Okay. Yeah? Continue? Okay. So, when two coherent waves propagate, that means move, when two coherent waves propagate together from two different sources, eventually their peaks will meet. We say the path difference is the difference in the distance each wave travels. So, in this example here are two waves, one from S1 and one from S2, and they move together and they're coherent, and eventually I think I should rewrite this a little bit, but we can point them at each other so that eventually they meet, or at least rather they're can you see here at P the two troughs meet at the same point. Okay, so right now if you look at this picture, we don't have them meeting yet, but here they do meet. In this picture here, here and here, they meet. Now, do they meet? Yeah, crest. It's so hard to see. Trough. It doesn't matter. Anyways, they meet. That's all I care about. But which wave has travelled further in getting to P? Travelled further. S1, yeah. So the path difference is how much further the wave had to travel before they meet. So in this picture, the reason it's 0 is because they both travel the same distance. And in this one here, the S1 travels more. Now, when you give the path difference, it's quite common and normal to give the difference as a proportion of the wavelength. So we don't say the path difference is 10 centimeters. We should say how much of a wavelength is the path difference. So I think you're right, Monica. I think it's a crest meeting a trough here. So perhaps I should reword this definition a little bit. It's not super clear. But you understand the idea that the path difference is how much further the wave travels compared to its neighbour when they meet. Yeah? Come on.
Is there lambda over 2 always?
Oh, no. And just in this picture was lambda over 2. Lambda over 2. Yeah, okay. So where's my path difference? When two coherent waves propagate together from two different sources and they meet, then, when two coherent waves propagate together from two different sources and they meet, then we say the path difference is the difference in the distance each wave travelled, and we express this in the form A lambda. In other words, we say how much of a lambda, or maybe I should say K lambda. So in this picture here, the K is a half. It's a half a lambda. Yeah. Okay, so you probably want to write the definition down here. This is a bit better. Or you can put in your own words. You can use your own words. This is the picture for it. Do you want to write it in your own words or what I wrote? When two coherent waves propagate together from two different sources and they meet, you don't obviously have to write pause, okay? You probably figured out what the pause function does. The pause function is when not all the text appears at once. You know, pause, that's what the pause is doing. Yeah, like PowerPoint, yeah. Except this is better. When two coherent waves propagate together from two different sources and they meet, then we say, the W should be small. We say what do you think alert does? It makes it red. We say the path difference is the difference in the distance between each wave travelled.
What language is this?
LaTeX. Yeah.
Oh, I could be for sure.
Please don't write pause down and alert. Please. It would be so embarrassing.
In the form
K lambda.
What?
Well, it depends on the question. The K is just some constant, so for each question it would be different. So in this one here, this is a 0 lambda. This one here, the path difference is a half lambda. A K is just a real number. K will be bigger than 0.
What does that mean?
Oh, it's how much of a wavelength. So if k is a half, it means the difference in the length is a half of a wavelength. Yeah. Where k is from 0 to 1. The dollar means maths mode. Make it maths. No. No. That's why I use this. Yeah, so what I'm about to say next is if k was more than 1, we only actually care about how far into the wavelength the difference is. So for example, if the difference in the path travelled was 1.5 wavelengths, we actually only really care about the half, not so much the 1. Because we're very much interested in how far into the next wavelength the difference is. Because this will tell us what happens when they meet. For example, in this picture, because the path difference is half a wavelength, then I know that the half a wavelength, that the, I need to try and picture this. Where's my wave earlier? I'll draw one. Whoa, that's a wave. That's a wavelength. That's half a wavelength. Yeah, so half a wavelength would mean that this would meet with the trough of its neighbour if there's a difference of half a wavelength. If you can picture another wave underneath this, but off by half a wavelength, then it means the crest is meeting with its neighbour's trough. So I don't care that it's 1.5 wavelengths, it's only the sort of how off in the end is it. Yeah. So half a wavelength is interesting because a crest would meet with a trough, if you can picture that. What about a quarter of a wavelength? What would a quarter of a wavelength? What would happen?
0.
A quarter of a wavelength would mean that this piece would meet with the 0 piece, the middle piece. Yeah? And for example, this piece here, what would that meet with? The one in the middle? A crest or a trough, yeah. And what else? What else is interesting? No, I guess the most interesting one is when it's a half a wavelength, because the crest would meet with a trough. Yeah? And the other interesting one, of course, is if it was 0 wavelengths, because then a crest would meet with a crest, and a trough would meet with a trough. And if it was 1 wavelength, well, 1 wavelength is the same as 0 wavelengths, because the wave repeats. So I suppose if we want to be even, we don't care about if the k is 1, because that's the same thing as being 0. So less than or equal to 0 and less than 1 is the 2. That's less than or equal to. I said it, the 0 being less than, I said it the other way. K is greater than or equal to 0. And k is smaller than 1. And we don't care if the k equals 1, because then we're back to 0.
So it's not total distance.
No, it's like a wavelength distance, I suppose. I'll put it in quotation marks. Not that you need to write it down. Okay. Okay, so like I said, half a wavelength is a very interesting case because a crest meets with a trough and a trough meets with a crest. And this kind of gives us our next idea. When waves combine, two things can happen. For example, if a crest meets with a crest, does it get bigger or smaller? It gets bigger. If a crest meets with a trough, it gets smaller. We call the interference constructive if the waves combine to form a bigger wave. And you can probably guess what this one means. Yeah. Got that? Continue? Well, I'm still the same slide. The next one is completely destructive interference. Yeah, that the waves combine to cancel each other. And that's interesting. Here, actually, that's completely destructive. The crest combines with the trough and we get nothing. This is actually what you might call nearly completely constructive. Because the waves are identical, the new wave is perfectly twice the previous wave. So this is like the extremes, completely destructive and completely constructive. You can cancel the waves or make them twice as big. That's the extreme points. And both of these have important applications.
What means you said just now 1 equals 0, 0 equals 1.
Oh, what I mean was here. Can I write it somewhere? Yeah. In this one here, we don't care if the k is 1. So for example, if we have a wave like this, and then I'll draw another wave which starts here. So the difference in the path is 1 wavelength. Well, that's kind of the same thing as a 0, because I can't tell the difference. If I start at the same point, 0, it looks the same picture. So I don't actually care if it's a 1, because when it becomes 1, it's like being 0 again, because it repeats. So that's what I meant when I said the 1 is like the 0. I don't care about the 1.
Okay.
Yeah. Does anybody know an application of destructive interference? Yeah, how? But what I mean is an engineering application. Like, what use could you make of this phenomenon? Yeah?
Radar or destructive radar.
Oh, very good, yeah. That could be possible, yeah. A bit more boring though. Give me a more boring example. Yeah. In factories, when they have loud machines, what they do is they try to make a sound which is the same as the sound of the machine, except there's a path difference of half a wavelength. When the sound from their machine combines with the sound of the factory machine on the factory floor, then it flattens out. Now, this process isn't perfect, so it'll still be loud, but not as loud. I think they do the same thing on planes. Because think about this, when you're on the ground, you can hear the plane engine, right? If the plane is low enough. How high up? Let's say you could hear the plane when it's maybe 1 kilometre high, 1,000 metres or 2,000 metres. You can hear the engine very loudly, okay? If you were on the runway and the engine was getting warmed up, you can hear it very loudly. When you're inside the plane, this is when you're closest to the engine. You're literally meters away from the engine, and it sounds the quietest. It's quiet enough that you can talk to someone. Although you step outside on the runway, you can't talk to someone if the engine is running. So I feel like they must have a sound system inside the plane that uses this process to cancel the sound of the engine. Now, of course, you can still hear the engine. It's not perfect. But next time you're on a plane, you notice how much quieter it is compared to when you were outside. And it should be louder because you're inside. Wow. You're closer to it, right? It's not like the plane is soundproof, because when the plane lands, or when the plane opens the door to let the wheels out, you can hear that. So it's not like the plane is soundproof and they have special soundproof inside of it, because then you shouldn't be able to hear anything outside, including the wheels coming down, you know. So I think they must use some system like this. I think so. Yeah. Continue? Yeah. Now, you might be familiar with this experiment.
Yeah.
Did you see this before?
Yeah,
Yeah.
What do you know of this experiment?
it sometimes act as a wave, sometimes act as a particle.
Yeah, but since we're not at that part of the course yet, we're only looking at waves. So the double slit experiment is important because it shows the behaviour of waves that is unique to waves. If I have one wave here, and the wave passes through two holes, it'll make two waves. These two waves combine. When it's brighter, the combination was constructive interference. When it's darker, the waves must combine to destroy each other, and it was destructive interference. In other words, you only get this if there's waves. If this wasn't a wave, if it was particles, ping pong balls, then you should only get two images here, one from each hole. But because we have multiple images here, it's actually because it's a wave and there's an interference pattern on. This is Young's double slit experiment, very important experiment. If the waves are in phase, in other words, if they're coherent waves, and in phase means that there's a zero phase difference, then we can have this image on the screen of the different patterns, the slits. We find that the wave produced on the plane will have maximum and minimums. So, for example, here, maximum, minimum, maximum, minimum, that the waves are combining and they're making maximums and minimums. So here, a crest from this wave must have combined with a crest from this wave to make a very big crest here. And what happened in this black area? No, actually. Crest with trough to make no wave. Yeah, a trough with a trough would be bright as well.
How can that be? Because they are exactly the same way. How can crest be with the trough?
Yeah, I'll have to draw it for you. I'll do my very best to draw this to help explain. Prepare yourself for an amazing picture. Let me just close this so I get full. I want to use all my video memory to draw this.
You can close the video.
I close the PDF, yes. Now just take out your 3D glasses. Good, good. Okay. Alright. Uh-oh. Breathing. Ah, okay. Right, my very best. Okay, so we have a slit, and a slit, and we have one source here, and we have our screen here. Now, this wave, I'm looking at it from the top, so I can't really draw it like this, because I'm looking at it from the top. So if you imagine looking at an ocean wave from the top, you can't really see the peaks and the troughs. You could see it when you're looking at the beach, you can see it, but when you're looking down from the sky, you can't see it. So the way I'm going to draw that is using different colours. So when I draw a blue, it means that's a peak. And when I draw a red, that means it's a trough. So you can imagine it going up and down like this. So peak, trough, crest, trough, crest. Oh, and by the way, since we're talking about it, what's the distance between these? How much of a wavelength? Well, think about it like this. I just said blue is a crest and red is a trough. So the distance, if you look from the sky, the distance between them is a half wavelength. Yeah. Okay. Next one. Trough. And then here, crest and crest. And trough and trough. Okay, so it gets interesting now when they combine. So here they've combined. A crest with a crest makes a crest. There you go. So like did I do that right? Well, hey. Okay. So look at this point. If you were looking at this from the sky, here you would see, here you would see a very big crest. Here you would see a very big crest, and here you have a very big crest. Now look at this point here. This should be cancelled. Here should be cancelled, and where you can't quite see it, but maybe earlier here, there it is there, and well, my picture's not perfect. There it is there, if you can imagine it. So this is moving across, and it hits the screen and makes a crest. This point, as it moves across, hits the screen and makes a nothing. It's a cancel. So if you do this very, very carefully, what you'll end up with is crests and nothing. By the way, if a trough meets with a trough, that's also very bright. It's only dark when it flat lines. So you'll get bright, dark, and so on and so on. Now, what you can't quite see in my picture is actually these are spreading out. So the distance here and here will be different for the next one. If I draw this again, this will be a bit bigger, and this will be here. This distance is actually bigger than this distance. As you move out across the edge, the distance between the crests on the screen actually increase, and it's actually because the angle here, as it's spreading out, you can imagine when the angle hits 90, it actually goes down to infinity, so it gets further and further and further and shoots off. Happy with that picture? Because I know I'm happy with this picture. Yeah. So this is the reason why we get this effect in the double slit experiment. Okay. Now, I think actually that would be a good point to leave it there. I don't know if you want to try and draw this. I recommend that you don't. Instead, there's excellent animations online showing this. You can see it happening in 3D. 3D.
With the glasses.
Not with the glasses though. But what I mean is people have done like nice little computer animations showing this. I know this is great and all, but it would be good to see the animations. Yeah. So I don't need you to draw this, but if you want, just take out your phone and just hit into YouTube animation of interference double slit. I'm sure you'll find something. Okay, we'll leave it there. So we have 1 hour, isn't it? Yeah. Okay. Oh, I closed it. The free. What did you want?
So we don't have to write anything. I mean, unless I know the title.
I think, yeah, maybe, guys, maybe you can just finish by just writing that sentence down. If two in-phase coherent waves are emitted from 2-point sources and then later superposed on a plane, we find that the waves produced on the plane will have maximums and minimums. Just write this down and then you can go. What room are you in next?
Oh, seriously?
Chemistry?
And then we come back here.
Yeah.
Seriously?
Can we leave our stuff here?
I don't know if there's someone in this room next.
Only 1 hour.
Huh?
Only 1 hour.
No, I know, but I don't know if people need to use this room.
What are we doing?
Can we still can hear the sound that two sounds are contrast each other with delay?
Oh yeah, we'll talk more about the sound and the two sound sources next time when we continue this.
You can still hear or?
Well, it's interesting because just like with the interference part in here, if you had two sound sources and you set it up just like in the interference where you have two sound and they're both coherent and in phase, so they both are the same sound, and if you walk across with the two speakers here and here and walk this way, you'll actually hear the crest and the trough. It'll get loud, quiet, loud, quiet, loud, quiet. And I actually did this in class with two speakers. If you look at my YouTube channel, you can see this. Guys, yeah, just before you go, if you want to look at my YouTube channel, there's a video, I can't remember what I called it, probably something stupid. I had two speakers, and both speakers had the same sound coming out of it. And then I had students walk across the back wall, and I told them to stop when they heard it loudest. So they walk across the wall, and then it would be loud and quiet. So when they heard it loud, they stopped, and then I said the next person said keep walking until you hear it loud again. And the distance that they were apart is actually the interference pattern, just like with the light, except a crest would represent a loud sound, and a trough, a dark spot would be no sound or quieter sound. So you could actually do this at home if you have two speakers with the same sound. Now you can't just play any sound. You can't just play like Nicki Minaj or something. You have to play. You have to play a pure sine wave sound.
Yeah.
So you could go to YouTube and you could type in test sine sound, and you can pick any frequency you want, and you can get that. That sound that it just sounds like a hum.
Let's do it.
Well, I can do it, but I need two speakers.
Oh, I have speakers.
But are they separate speakers? Can you separate them? Yeah. You have two speakers, so I could put them any distance apart.
I have one speaker. I have one speaker.
Does anybody have two speakers that work together?
What about
or is everybody's speakers connected? You can't separate the left and the right. I need to have two speakers where I can separate the left and the right. No. So if you connect to the laptop, it will connect to this. You can connect two speakers to the laptop?
No, unless they are from the one.
Yeah, this is what I need. I need two speakers for the same laptop.
Wait, you're doing my cousin.
What?
He plays guitar.
No. He used it.
Nobody has two speakers?
No.
Anyone? I mean, even though I have these two speakers, that I can connect two speakers in one device because of the Bluetooth.
You can connect two speakers on one device, or you can't?
I cannot.
Are you sure?
I think so.
Okay. Well, if anybody does find out how to connect or has two speakers that can connect to one laptop, if you bring it into class, we can do this, and we can hear the interference pattern. Yes. Wait, hold on. Let me just close this.
Okay. You said you're gonna do the lab next week.
No, I didn't. I said I might do it next week if I can't give you the maths.